Complete tutorials on CAN protocol. CAN protocol part 3, OSI layer and ISO standards. Before entering into these OSI layer as well as ISO standards, we'll have a quick look on the features and benefits of the CAN protocol. Here, the feature CAN has a multiple master hierarchy, that is for building an intelligent and protecting system. So these are all the things that you have to know, and you can explain to others. Even you can use these concepts in the interview perspective. So the question will be how the CAN multi-master will bring you the protocol's efficiency. So here the answer is for building intelligent and redundant system. So this is why the multi-master concepts has been brought into picture. Then it provides transfer rates up to 1 Mbps per second. That is why this 1 Mbps. The benefit is for adequate real-time response in many embedded control application, not only in the automotive application, also in the home appliances as well as the industrial, even nowadays for medical equipments. It allows 0 to 8 bytes of user data per message to accommodate diverse design requirement. This has been limited to 0 to 8 bytes of user data per message. Then it puts a multiple transmit or receive message boxes at each node and assigns each an identifier. This concept has brought for the flexibility in the system design. Then eliminates the it can has a feature of eliminating the address of transmitting and receiving nodes in the data. So this will save the bus bandwidth, it simplifies the software, and it allows the simultaneous transmission of node to node and broadcast the messages properly without any data loss as well as time delay. It causes receiving nodes to filter the messages based on the assigned identifier, that is message ID. Why this message ID? What is the purpose of this message ID? Yes, to simplify the node hardware and software, to permit the message prioritization, to allow the hardware to arbitrate the CAN bus. These are all the benefits that CAN brings you. CAN has a feature of automatically retransmits messages if corruption occurs. Yes, for accurate communication even in noisy environment. So this is how the CAN has retransmits, because it will not, if the corrupted data is not trying to retransmit, or if we try to send an error message, then it will be the data loss as well as the time will consume. But here CAN will try to retransmits, it will try to diagnose, it will try to correct it, and it will send the corrupted message without any data loss. Then it provides a error detection, signaling, and fault confinement. So these are all the three error handling techniques CAN provides: error detection, signaling, and fault confinement. So here, to ensure the high reliability in reliable network operation, these error handling has taken place. So this error handling has brought the unique property of the CAN has it's a high reliable in its operation. Okay, we'll get into the OSI model, how the CAN has been and where it is. The CAN is a closed network, yes, of course. No need for a security sessions or logins. So there is no logins. If you want to use CAN protocol, you don't have any logins or you don't have any authentication. Then no user interface requirement. So there is no user interface also. Here, how the OSI plays in its CAN, the physical and data link layer in silicon. So this CAN bus has been into the OSI model with the two layers, the physical layer and data link layer. And application is, for your understanding, application layer is like OBD protocol, UDS protocol will takes place here, and CAN layers have data link and physical layer. So this is how how the transmission works. These are all the lower end of the OSI layers. See here we have CAN in OSI. So these are all the higher layer protocols. So application layer, so I said UDS will take place here, and presentation, session, transport, network, data link, and physical. So these are all the 7 OSI layer. Okay, so here the CAN protocol is placed in these two. So how it works. So before that, yes, we'll still start with this physical layer. A physical layer is nothing but the it will invoke the signal that whatever we are sending. So for example, if I am sending some data to the CAN, yes, of course I will send through analog method, analog way. So if I am on ECU, I'll definitely send, if I am pressing the pedal, that is acceleration pedal, I'll press, and the signal is analog. Obviously the analog signal has to transmit in a digital way, so that sensor will take care. So by using the technique called modulation, the modulation will convert the analog signal to digital signal. Then the digital signal will taken into the physical layer of the CAN protocol. So this physical layer of the CAN protocol taken care for the media transmission, signal and binary transmission. So the transmission of these messages or signals can be taken care in the in terms of bits. So that is what the physical layer really do. So for a simple understanding and the better understanding, so the physical layer is nothing but the wire, the twisted pair of wires. Okay, so that's what here they have given the bit encoding. So that's what I said, there's a modulation, the encoding and decoding, the bit timing, synchronization and the driver receiver characteristics. So these are all the main work of the physical layer will do. And the CAN protocol also have deal with the data link. So the data link layer, it's a data link is a MAC and LLC, it's a physical addressing. So what it does, it does the acceptance filtering. So what are the messages the physical layer is sending? Yes, of course no protocols will rawly, it will not send in a raw way. So it will definitely has to filter some of the noises. So it will filter it, and it will, if there is any overload, it will also do the overload notification, and if there is any loss, it will do the recovery management. And here in MAC, the data encapsulation and decapsulation, there is, it will protect the signal without, of course we are entering without any authentication. So it will give some encapsulation, that is hiding the logics of the transmitting signals. And after that, the frame encoding, bit stuffing, destuffing, everything. The MAC, that's a medium access management, will handle the error detection, error signaling, acknowledgement, serialization as well as deserialization. These all the things can be, only these two layers will complete these many process. Hence the data is more and more accurate and reliable for the users. So this is how these two works. And here this physical layer will works with the bits, and the data link layer works with the frames. So this is how the two things has been happen. So if we are roughly see the OSI layer, still after these sent, then it will goes to the network. Yes, of course in all the issues there will be the network. So the network has to determine the path which has to be sent. So the path can be determined by the IP address. Of course, if I am sending you some mail, the mail will reach your IP address, then you can read out the mail. So in the same way, the network has to determine the path by means of the IP, that is a logical addressing. After that, that messages can be sent by means of the packets. Even if you open your PC, you can see how many packets has been received, how many packets has been sent. So yes, this is what the network protocols always deals with the term called packets. So next is a segments in the in transport protocol. The segments has to transport, that is the end-to-end connection and the reliability. Then the session, so these are all not in a part of CAN protocol. Yes, of course you can understand. So once the segment has been transported, all the other three layers will transmit it as a data. So it will transmit in a session layer, it will transmit as a inter-host communication. And once this session layer completes, the presentation layer, it will send as a data representation and encryption. And here also one more encryption has been happens. And here again the data has been done as a network process to application. So this is the application layer. So this is how the OSI layer happens, and these two layers only the CAN protocol works. So these are all can be taken from the, you can if you want to go more in depth, you can go through this ISO 11898. Okay, so this is how the OSI and ISO OSI concept is done. And here 120 ohm, yes, why this 120 ohm? Always that CAN has to be terminated with the 120 ohm resistance, the each end. The two wires driven with the differential signals is CAN high and CAN low. So this has to always be terminated with the 120 ohm resistance to, yes, to minimize or to completely avoid the signal reflection, so that there will not be any noise or harmonics in the CAN transmission as well as the reception. So this is one of the most common and cheapest implementation is to use a twisted wire pair. So as it is simply twisted wire pair, so there will be the noises as well as signal reflection. So this can be reduced, or this can be completely avoided by the cheapest implementation, that is 120 ohm resistance. As you know, the resistance in the market, it cost around 2 rupees or 3 rupees to Indian currency. So it is so cheap to implement. So these two resistors around within 5 rupees of Indian currency, you can just avoid the signal reflection. So this is the cheapest implementation so far, can give you the better efficiency. The number lines are then called can high and can low. The two bus lines, that is can high and can low, are driven by nodes with a differential signal. The twisted wire pair is terminated by terminating resistor at each end bus, typically called as 120 ohms. So the 120 ohm resistance has always been kept. Yes. So this is CAN and EMI. Due to the differential nature of the transmission of CAN is insensitive to EMI, that is electromagnetic interference, both bus lines are affected in the same way, which leaves the differential signal unaffected. So as the EMI has been, the both ends are the affected, so it will leave the differential signal as unaffected. That is what the nature of the CAN transmission. So here you can see here node A, node B, node C. Node A is trying to transmit something, the can high and can low, and if the EMI comes, the 120 ohm resistance is always be make the signal to be unaffected. So to reduce the sensitivity against the EMI even more, the bus lines can do additionally with shielded. So to avoid this, we can shield it. So that's what the CAN has comes into shielded pair. So this is one of the interview question that can be asked, why the CAN has to be a shielded pair. Because the reason behind this shielded is, it can be additionally, it can be a sensitive against the electromagnetic interference. This also reduces the electromagnetic emission of, so it's not only avoids the electromagnetic interference, it's also reduces the electromagnetic emission of the bus itself, especially the high baud rates. So high baud, whenever the transmission of data is a high baud rate, it will always try to serve against the EMI, that is electromagnetic interference as well as the electromagnetic emission. So this is how the CAN and EMI, that is electromagnetic interference, relates. So in simple, CAN will always have a effect, CAN twisted pair will always have a effect of EMI. To avoid this EMI, we will have the shielded, that is the shielded wire. Then standardization, how this ISO has standardized. So just you have to be very carefully listen these concepts. So these are all the standards that you have to follow when you start with the CAN. So the vehicle bus system application can be separated into three categories according to the real-time capabilities. So class A, class B, and class C. So class A is a low speed bus, class B also low speed bus, and class C is a high speed bus. It with the data rate up to 10 kbps, example for the body of the control application. Okay, so it's up to 10 kbps, it's not beyond 10 kbps. And class B, it's also low speed, but the rate is a little bit higher, it is 10 kbps to 125 kbps, example for the dashboard as well as diagnostics. So this class B is more than enough for the dashboard as well as diagnostics. Then here class C, so for high speed bus with the rate of 125 to 1 mbps for real time application like engine management, gearbox, ABS, etc., because these are all the critical modules comparable with the diagnostics or dashboard. So yes, so this is how the CAN has standardized the three ways, three categories. It's class A, class B, and class C. Here we can see class A, class B, and class C. So we have the graph that clearly mention, here it is up to 10, and here it is up to 10 to 125, and here up to 125 to 1000. So engine management, gearbox, ABS, dashboard, then body control. And this is the low speed bus is the 115192, and the high speed is 11898. So for use of CAN in vehicles, two standards have been defined for the bus interface. So it is, of course, it is a low speed and it is high speed. I will not use this, I will only use this, it's not a concept. So we have to use both low speed as well as high speed to maintain the economy. Of course, this low speed bus will not make you more delay it will make the fraction of seconds or sometimes seconds delay, but yes, the delay is necessary for the application that we are going to use in the car, that is in the vehicle. So low speed bus can be used for wherever the delay needs or delay occurs to transmit the data. Fine. The bus levels according to the ISO is 1189, 11898 is the these are all bus levels. According to this, the resistive bit is represented by the both CAN lines driven to a level is about 2.5 volt. So this is the blue color is the resistive level and the green color is the dominant, that is a dominant level. Here, the differential voltage between the CAN high and CAN low is around 0 volt. Here, the difference is 0 volt, the CAN high and CAN low. See here, once in dominant, in resistive, the difference is 0. In dominant, it opens, the CAN high is going to 3.5 and the CAN low is going to 1.5. So the difference is around 2 volt. That's what it's mentioned. The dominant bit is represented by the CAN high going to about 3.5 and the CAN low going to about 1.5 volt. This results a differential voltage for dominant bit is 2 volt. So this is another interview questions they can expect. So how the dominant bit of the differential voltage for the dominant bit is 2 volt. You can just draw this graph. So initially in it will start with the resistive bit, both CAN high and CAN low. So once the dominant bit comes, the CAN high goes to 3.5 and CAN low go to 1.5. So the differential voltage is 2 volt. So this is how the CAN high and CAN low, the differential voltage is 2 volt has been derived. Fine. Here again, get back to the CAN physical layer. So this is the reference we have taken, the canbuskit.com. Fine, it's attribution. It's attribution that we have given. Fine, it's a physical medium, so two wires terminated at both the end by the resistor, as we have seen. Let's see how in more in a simplified way. The usage, so the main usage of this is to reduce the weight, reduce cost, fewer wires, and increase the reliability. Here this is the conventional multi-wire looms. So see, these are all the these are all the core components. Here you can see engine, transmission, cluster, then lock windows, security, then BCM module, ECM module. See, a number of wires have been connected. So these wires is the conventional multi-wire looms that is have a drawbacks of the weight. It's around 70 kg of weight. So it really it decreases the mileage of the car, as well the efficiency of the engine also goes down. But here the can comes. So see how simple this architecture is, and it's very simple, and the weight also comparably very less, so it can increase the mileage and efficiency of the system. This is how the physical layer has been brought here in the can. Here one more physical interface. So how this works, the dominant is bit is low voltage line. Here it's a low voltage line is a dominant bit, and resistive is high line, it's a high voltage. So this is a dominant bit, there is a high, and it's a resistive, a dominant bit is a low, and resistive is a high. The bus must be terminated. Yes, it will be terminated as a 120 ohm resistance. The most common physical layer is C. This is a standard, and here if we see, we have the node C, node node E. Sorry. Okay, if electrical isolation from the network is desired, it typically is done here. So electrical isolation, the shielded pair twisted has been implemented here. So here the typical node, the MCU, it's a bus transceiver. It can communicate in this way. So here if we have bus, it will go to the CAN high and CAN low, again CAN high, CAN low, CAN high, CAN low. It will transmit the data in this way. If this bus transmit the data here, then it will transmit to here, and it will goes here to the transistor. So we'll have look with this node. If this C node is transmitting, then it will goes here, the bus transceiver it receive as, because transceiver is nothing but transmitter plus receiver, it will receive, then it will send to the MCU microcontroller unit, then it will process the data, it will transmit again, then it will again communicates with the CAN high with respect to CAN low, then it will give its response. So here also in the CAN bus receiver will receive the node C, then the MCU will process the data. So this is how the physical interface works. Then here the physical layer implementation. So the physical layer implementation is, see, Here we have, this is a circuit of CAN high and CAN low. Here the this is a renaissance one of the microcontroller for in-vehicle applications. The ISO complained the high-speed CAN bus up to 1 Mbps. It's active standby modes. So over temperature detection, over current detection. There is, these are all the microcontrollers has been programmed in the CAN. So over temperature detection, over current detection, optimized EMI performance, then TX mode inputs compatible to 3.3 volt. So if any of these range is being gone over, so then the error message start to transmit in the CAN physical layer. So here CAN high, CAN low, it will always sends to the transceiver, that is here transmitter, it is here, it is receiver. So if you see this as a whole, it's a transceiver. If it is separate, then this will receive here, then this will be the output, then this will sends to the microcontroller unit. And this yes, of course this will send to the micro, that we know. But if any of these ranges has been gone beyond, then this will comes here, it will directly comes here. The protect function, it will all keep on checking the current, voltage, then temperature, then the EMI interference, then the active standby mode. So everything, these are all the, these parameters will be monitored here. If anything goes wrong, then it will take it back, and it will just protect the vehicle, that is it will protect the ECU. It sends the voltage into the ground, so that here there will be no receive message. Hence the count, the REC count will decreases, increases, then it will transmit the error. So this TEC REC will be seen in the next upcoming tutorial, but as of now you just understand, it will send here, it will process, if everything is fine, it will send to the MCU. If not, this will comes into picture, it will just take it, then it will ground it back, and the error message will be transmitted. So this is how this works, this physical layer works. So the continuity of this tutorial will be continue the next, that is the CAN protocol part 4, so characteristics and signal flow. So yes, I guess you got something in this tutorial. So for the main intention of this tutorial is you have to be more and more aware from the scratch till the end of the in the CAN protocol. So we'll get back to you with the next tutorial, that is on characteristics and signal flow, that is CAN protocol part 4.